So I must begin to tell you that I will pick up on some of the themes that Hancho Sensei was touching on towards the end of his talk. And I will in particular try and weave together some philosophical questions and conflicts, as well as the science behind global warming and climate change. So the topic really is the role that the oceans will play in the coming decades and centuries, perhaps, and whether it will become a victim of global warming, or perhaps there's a way in which we might be able to use the ocean to help us to delay this process until the global society can come up with long-term solutions. But I must begin with some other thanks, in addition to the thanks that Dr. Hancho presented. I would also like to say that it has been most enjoyable over these past several days to meet with my fellow speakers, with the graduate students, with the members of the organizing committee. I think we have all become very close friends in a very short period of time, and I look forward to continuing those friendships and collaborations in many years ahead. The other thing I need to describe and disclose is that in the top theme for the conference, it mentions standing or learning from the giants or on the shoulders of giants. And despite my height, I am not one of those giants. I am not a climatologist. I have a PhD in oceanography, but the most of my career has been spent in biotechnology, and only recently have I returned to the field. So much of what you will see in my talk is highly referenced to primary scientific literature and other publications. If you get a copy of this, it can serve almost as a syllabus for a course. But these are the true giants who have built all of the foundation for what I will touch upon. And my role here is simply to weave together the story. However, I do have to point out one particular giant, which is Hancho Sensei, whom I have known now for some 40 years. When I first went to Woods Hole as a graduate student, he was my very first advisor. And this handsome young man you see here, peering over Emperor Hirohito's shoulder at the microscope, was my teacher, mentor, shipmate, colleague, and friend on a very personal level. But for the world, he has truly been a visionary scientist, a tool maker, a global thinker, a humanitarian, and an entrepreneur. And without him, I would not be here today. Thank you, Sensei. So, to continue, I will give you an overview of global warming and climate change at a very simplistic level, given the time. And then the various philosophical themes I want to weave into the discussion are based on a publication called The Tragedy of the Commons, which deals with the topic of who's responsible both for causing the climate change we now see and who will be responsible for correcting it or stopping it. It also deals with a problem known as the prisoner's dilemma, which is the struggle that we face currently of individuals, nations, states, the society, for coming up with a common solution to this problem. And then another story based on something called civil disobedience that you'll hear about, which brings us to a very personal level of what decisions we choose as scientists or as citizens in contributing to help solve this problem. I'll also talk at the end about something I call carbon sequestration. That's not a typographical or spelling error. This is a twist I have on how to use the ocean to help buy time by burying carbon dioxide in the deep ocean, similar to what Hancho Sensei was describing with the biological pump. And at the end, I will talk a bit about what individuals can do to join this process and contribute to the process. So to pick up first on the causes of global climate change, I'll first talk about a very simple view of how to understand this process and why it's occurring, which I call the Carboniferous period in instantaneous reverse. And then I'll cite a number of references which I would recommend to you as excellent sources of background to familiarize yourself with the nature and the breadth of this problem, starting with An Inconvenient Truth, the film that Al Gore developed, which was the wake-up call for global warming. A very critical book called Storms of My Grandchildren, which is a book that I sincerely believe everyone should read, that I will talk about a recent article that's very disconcerting, but again, provides a very simple way to understand the threat we face with several numbers that was published just this past summer about the terrifying new math of global warming. And if I have some time at the end, I'll show you a short video clip from a documentary film that is now in theaters, at least in limited numbers in the United States, and hopefully will become available worldwide, about the rapid changes and melting of glaciers. It's called Chasing Ice is the name of the movie, and it comes from a program called the Extreme Ice Survey that I'll discuss. So the Carboniferous period is a geological period during which much of Earth's coal deposits were formed, and it occurred starting some 360 million years ago to perhaps 300 million years ago. So a period of 60 million years in geological time, during which all of the dead plant and animal material that was buried in the sediments and then eventually under very high pressure for millions of years was converted into what we now see as coal, oil, and gas. But as Hanjo Sensei mentioned, beginning with the Industrial Revolution in about 760, so some 250 million years ago, almost an instant in time, we started burning initially coal and later oil and gas, essentially digging up these deposits that were formed millions and millions of years ago and converting them back into carbon dioxide, where it all started. The problem is the difference in the time frame. It took 60 million years to make all this coal and deposit all that carbon dioxide, all of which came out of the atmosphere by photosynthesis. So we sucked all the carbon dioxide out of the air over millions and millions of years and buried it in the ground, where it didn't affect the climate, it didn't contribute to global warming. But now we are digging it up and drilling it and burning it at an alarming rate. So in only 250 years, we have burned a significant fraction of this and converted it back to carbon dioxide, more or less instantaneously releasing all of this buried carbon dioxide into the atmosphere. So a very simple way to view this, in the cartoon, the nice sunshine shining on the plants, fixing carbon dioxide from the atmosphere. The dinosaurs and the plants all died and were buried in the ground under millions of years of pressure to convert it into coal, oil, and gas. But what we've now done is released the pressure. We've taken the cork out of the champagne bottle, and all of that CO2 is back in the atmosphere again. It's like the ghosts of the dinosaurs have come back. Godzilla almost looks like some coal and oil and flaming thing. And I somehow wonder whether perhaps these ghosts of the dinosaurs, which are now haunting us as carbon dioxide in the atmosphere, were the yokai that interested your founder. I'm not the first one to invoke Godzilla in this context. This was a cartoon from Christian Science Monitor showing Godzilla as the big threat of global warming. And he's chasing the human being into the arms of Frankenstein's monster labeled nuclear power. And unfortunately, this is something we have to face today, and obviously is a particularly sensitive topic here in Japan with the crisis that we've had to endure for the last several years. But the reality is that the world must truly embrace increased use of nuclear power if we are to solve global warming. It will be one of the key components. But it will be very difficult to convince everyone that we should go back to increased use of nuclear power because of accidents like the one that just occurred after the tsunami. So this is one of those conflicts that we now have to resolve as a global community as to which do we rather face, the global warming Godzilla or the threat we have from the nuclear power. So going back, why does all this extra carbon dioxide in the atmosphere really matter? You know, it's a gas that's not poisonous by itself or anything, but it is what's called a greenhouse gas, which means that it absorbs incoming solar irradiation of sunlight, which warms the atmosphere by trapping that heat, and then transfers that heat to our oceans, to our land, and it warms the entire planet. And as was mentioned by Hanjo Sensei, the carbon dioxide also dissolves in our oceans, the same way the carbon dioxide is dissolved into champagne or in your Coca-Cola. And in the process, it lowers the pH and makes it more acidic. The big problem with that is that it begins to dissolve the very shells of the organisms that are critical to sequestering carbon, and they make up much of the biosystem or the ecosystems that we're interested in. And later this afternoon, you will hear a very detailed presentation of this by Dr. Sua, who will explain it much more. So this figure you've already seen, known as the Keeling curve, which traced the increase in carbon dioxide in the atmosphere beginning back in just before 1960 by measurements away from cities and other point sources of carbon dioxide at the very top of Mauna Loa volcano in Hawaii. And this was done by Keeling, who worked at the Scripps Institution of Oceanography in California and San Diego. This is the Scripps Pier in the background. And Roger Revelle, who was head of Scripps at the time, took a sabbatical leave and taught for a year at Harvard University. And what you'll see in a moment is an interesting coincidence in time. So he was basically there 10 years after they started collecting data in the late 1960s. Revelle was teaching at Harvard. Another thing just to keep in mind for a little later in the talk is this number 350 is 350 parts per million of CO2 in the atmosphere. And I'll come back to this organization called 350.org that references this point, whereas we're closing in on 400 parts per million currently in the concentration. So it happened that there was a senior at Harvard who took a seminar class from Dr. Revelle and saw this Keeling curve for the first time. And that led to a lifelong interest in environmental problems, and in particular to the global warming problem, and led to the production of this movie, An Inconvenient Truth, which is a most appropriate title. The truth of global warming is real. It is also tremendously inconvenient for many, many reasons, which is why it will make it so difficult for humanity and the population of the globe to deal with the problem. So this film by Vice President Al Gore, almost President Al Gore, won an Oscar, Academy Award, with the rest of his producers for the film, and he also shared the Nobel Peace Prize in Science that year for this. So this was truly the first large, broadly available wake-up call for global warming. And I would recommend that you all rent or watch on the internet this movie. It's now 6 or 7 years out of date, but it really will give you a broad foundation and perspective for the problems of global warming. If, however, there is only one thing you have time to read, it is this book that I would recommend, Storms of My Grandchildren, by Jim Hansen, who is the director of NASA's Goddard Institute for Space Studies at Columbia University. He is one of the most prominent climatologists who has been sounding the warning about global warming for many decades. And he wrote this book inspired by his 2 grandchildren, concerned that in the future they would look back and say, "Grandpa, why didn't you stop this?" So this book contains very simple, again, intelligent lay audiences can read this book and you will understand the scientific foundation and all of the reasons why we can be absolutely confident that global warming is real and that it is caused by mankind, not by natural phenomena. So please, if anything, read this one book. Another interesting source comes from Bill McKibben. Bill has been a long-time environmental activist, and he is the founder, I mentioned on that chart, of 350.org, which believes we actually need to reduce carbon dioxide concentration and bring them back to at least 350 parts per million or less if we are to avoid the long-term consequences of global warming. He published an article in a very authoritative scientific publication called Rolling Stone, which usually covers rock bands and such, last summer, which talked about global warming's terrifying new math with three simple numbers that help you understand this problem. So the first of those numbers is 2 degrees centigrade. So this is the amount that the scientific community has reached somewhat of a consensus on, is the maximum increase that we can allow for the average global temperature change to avoid the serious consequences of global warming. It doesn't seem like very much. Within a single day, our weather can change 10 times this. We can have 20-degree fluctuations within a single day, which is weather. But we cannot allow the entire globe, on average, to increase by more than 2 degrees centigrade if we're to avoid global warming. The frightening thing is we've almost halfway there. The average temperature since the pre-industrial age of the globe has increased 0.8 degrees centigrade. So there's not a lot of room left. The next number is another one of these hard to get your head around or imagine numbers. 565 gigatons, 565 billion tons is the estimate of how much more CO2, is how much more CO2 can we generate by burning coal, oil, and gas and putting into the atmosphere to avoid exceeding this 2 degrees centigrade limit. So this is the total we can burn. So we've got a lot of time still to generate this much, but it's still small in comparison with this number, which is the scary one. 2,795 gigatons. That's 2.7 petatons. It's an unbelievable number. But this is the amount of coal, oil, and gas reserves that we already know exist and documented by the countries that are oil and gas and coal producers or by the companies that own these reserves. They have already accounted for how much stuff is still in the ground that they own or can extract in the future. And this number is 5 times the limit. So this is the stuff we already know. It doesn't include some exotic sources like tar sands in Alberta, Canada, gas derived from fracking, and other ways in which the oil and gas industry can go and find still unexplored deposits. And so the conclusion that we have to draw from this is that most of this amount of carbon has to stay in the ground forever. We cannot burn it. We can never use it. It has to stay in the ground if we're to hope to avoid ever exceeding this 2 degree limit. The problem that creates is that the value of the coal, oil, and gas industry is some $27 trillion based on this. This is their reserves, okay? This is what I have in the bank, so my stock price should be very high because you know I have all this that I can dig up and sell to you later. But if we now tell them, you can't, what does this do economically? So this all came from a report from an organization called the Carbon Tracker Initiative, which talks about carbon bubble. Carbon bubble is similar to the real estate bubble or the banking bubbles that we have seen that have collapsed economies. So how does the world compensate or adjust when there's $27 trillion sitting there that wants to be money? And we tell them, no, you can't make money by digging that up and selling it to us. It also causes the problem that $27 trillion of potential valuation is very interested in maintaining the status quo. They are the last people who want to see this left in the ground. And they will spend a significant fraction of that money to ensure that they can continue to practice their normal business practices and keep us burning these fossil fuels. So this is a map from that report that shows sort of by country in this particular view the different components. So in the US, we've got lots of oil, less coal, and a little bit of gas, and it's reversed in other places. But you can see who owns all these things and where they're located. There are other tables that actually show the state-owned oil and gas companies or the private companies that control this. And so it's the Exxon and Mobils of the world that are the ones that are going to try and prevent us from stopping them from making money from these assets. And so that's led to very deliberate efforts to confound and confuse the public, to somehow make people uncertain that this is real or that we are causing it and it's not some natural thing. Very similar to what happened in the tobacco industry when it was very clearly determined by the scientific and medical community that smoking cigarettes caused cancer. The tobacco industry spent millions and millions and millions of dollars trying to convince the public it just wasn't true. And they are now doing the same thing on global warming. So Naomi Oreskes and Eric Conroy wrote this very interesting book to sort of bring this to light so that the public can really understand what's going on behind the scenes. They've also published scientific publications. There's Naomi again in Global Environmental Change fairly recently. This is a 2012 publication dealing with the same problem, and it has a lot to do with how we practice science. Scientists are told to be rational, unbiased, conservative, not overinterpret your data, not make hysterical, claims based on your research, to evaluate the evidence, to look rationally at things. But that is, on the one hand, the way we've always done business. But now if you have a deliberate group of people willing to spend enormous sums of money to cause confusion, they don't need to follow the same rules at all. And that is the problem we've created. And this paper and others begin to explore whether or not scientists need to begin to act and behave differently to counter these other forces. Another version of that story is told by Michael Mann, shown here, in a book he's recently published called The Hockey Stick in Climate Wars. He is one of the climatologists who was singled out, and something you may have heard of called ClimateGate, where the emails from an entire group of climatologists were put up on the internet and then edited selectively to appear as if they were doing bad science or doing other things wrong. And he was at the very center of this. He was the lightning rod in this. His earlier work had... His earlier work had been trying to use tree rings as a method to try and get the paleoclimate data to support the increase in anthropogenic global warming. And so his data and the work that he was doing was targeted by those who want to confuse the public and lead them to believe that this is bad science. Well, just this month, another study by Marcotte has essentially taken man's data set and extended it even further, going back over 11,000 years in our records to show this graph. So the man reconstruction from the tree rings is this sort of noisy-looking gray line here that actually trends down until, if you go back 250 years, the beginning of the Industrial Revolution is right sort of at the bottom of this. We were actually at the end of something called the Little Ice Age, and the world was actually cooling off, and probably would have continued this downward trend of cooling were it not for man starting to burn all that coal and oil and gas, which has now resulted in this incredibly rapid spike in the temperature. So this more recent paper by Marcotte used isotopic measurements from samples distributed globally, including many marine samples. It gives a far more comprehensive picture. And their trace, which actually goes way back further, gives you a sort of smoother sense for this, but reconstructs and recapitulates exactly the same shocking increase, so far above anything that's been seen before as far back as you want to go. So this is real, it's caused by man, and it was caused by us beginning to burn fossil fuels at the start of the Industrial Revolution, only 250 years ago. Another excellent resource that I would point you to was a November issue of Nature from last year entitled After Kyoto. The Kyoto Protocol was the global environmental protocol under which nations were operating, where they pledged to reduce the amount of fossil fuel they were burning and the amounts of their emissions. It expired in January, has now been extended to some degree, but this series of articles in Nature highlight many of the different components of this problem. This particular graph, entitled Hot Air, shows the amount of carbon dioxide introduced into the atmosphere at a couple of key time points. So in 1990, it was was about 23 gigatons, or 23 billion tons of CO2. 7 years later, that had only increased from 23 to about 24 and a half. But between 1997 and 2011, we're now up to almost 34 billion tons per year of carbon dioxide. The slope of this is going up. It's not linear, it's an exponential curve. Things are getting worse fast. This plot, awash in carbon, each of the little, it's too small, I'm sure, to read, especially in the back. Each of these little figures around the circle is a country. And by country, the size of the bar indicates the amount of total energy. So here is the United States. We're the worst culprit. We generate and use more energy, closely followed by China. Actually, they show slightly larger. So they've exceeded us. The colors of these bars, if you can make them out, are the source of the energy. So the black is coal. So this fraction in the US is generated from coal. But if you look at China, it's almost all coal. China last year burned more coal than the rest of the world combined. The yellow component up here is nuclear. And interestingly, if you go over here to France, you can see it's almost half nuclear. There's almost no black there at all. So France really is a model. Japan, if you're interested, is right here. And there's your yellow nuclear, some coal, gas and oil in the middle. As I said in the beginning, the conflict between Godzilla and Frankenstein, France, which generates so much of its electricity and power from nuclear, is really a model for where we need to move to address this problem. So if you start looking at, where does this all come from, the world's largest CO2 producer is the Taichung power plant in Taiwan. It has 10 different units which combined burn almost 12 million tons a year of coal and convert that into CO2. But they're not alone. If you go to Europe, this is the Welsh power plant in Poland. This is Europe's largest producer of carbon dioxide. And you can see the coal fields that have destroyed the landscape in front. And of course, China now, about 80% of their electricity is derived from coal and increasing. They're continuing to build new coal-fired power plants at an alarming rate. We have to rid ourselves of our appetite for coal. And the problem is the coal, oil, and gas industry will stop at nothing to keep finding and extracting these reserves. In the Appalachian Mountains in the eastern part of the United States, they remove the entire top of mountains to get at the coal reserves. And they just dump the waste in the rivers and valleys nearby. We are now seeing these efforts to extract oil and gas from very unusual deposits, doing what's called fracking and whatnot. And there's a key issue right now of the Keystone Pipeline, which is proposed to be built across the United States from Alberta, where they are extracting oil from tar sands. And this pipeline would then carry that crude oil to the refineries that exist in the Gulf of Mexico, the Texas and Louisiana coast. The initial permits were blocked, and President Obama will now need to decide whether or not to permit this to exist, which will be one of the keys as to whether all of that carbon dioxide will come out of the ground in Alberta eventually. Another key factor in this is how long it takes before the world decides to take serious action. So the longer we delay in efforts to reduce carbon dioxide emissions and reduce fossil fuel consumption, the bigger the problem we face and the greater risk that we will exceed that 2-degree limit. So both of these papers deal with the timing dimension of that. And another one actually tries to factor in global costs into the equation. So the economics community are factoring into this as well. But the consensus is the longer we wait to try and do something, the greater the risk, the greater the cost. It would be to everyone's benefit to begin now to seriously reduce this. And one of the ways of doing that is to tax carbon as a pollutant in some ways. And there are various schemes. You've perhaps heard of cap and trade and carbon credits and carbon taxes. But I would point you to, again, that book, Storms of My Grandchildren, which explains the differences in these and why the only one that really makes sense is a flat carbon tax. That these others turn into what at least in English, we call a shell game, where you hide something of value under one of these 3 shells, and then move them all around, and you're supposed to guess, where is the value. And so this is the problem with trading cap and trade carbon credits. I get to burn all my coal I want because somebody else is planting for us, and so they're going to suck carbon dioxide out of the air, and so I get credit for their trees. But how I sort of keep the balance there accurately is extremely complicated, and this is the only way that it really makes sense. So during the elections, it was very scary that climate change was not a topic ever discussed in any of the debates. It was never discussed anywhere during the recent election campaign. But now that the election is over, Obama has come out fairly strongly saying that he's going to take action, and it will be important since we are the major, or one of the two major consumers and producers of this problem, as to what kinds of leadership we take in that arena. So where did this all come from? Who was responsible for this? And I would point to a very interesting paper by Garrett Hardin that published back in 1968 entitled A Tragedy of the Commons. And although the central theme, he was worried about population explosion, which is just as relevant today, he was worried about nuclear escalation during the height of the Cold War, but he also touched on themes that are highly relevant to the climate problem. And that is, the atmosphere of our Earth is owned by no one, but used by everyone. The oceans are owned by no one, but used by everyone. They are a common that everyone has access to. Everyone is responsible for causing the problem, and everyone will be responsible for solving the problem. And he deals in a very interesting sort of philosophical way with the fundamentals of those issues. And it then leads to something that's known as the prisoner's dilemma, which is this struggle for how we decide to cooperate as a global society. The notion of this problem that I'll describe in a moment was initially developed by Melvin Drescher and Merrill Flood, working at a U.S. think tank called the Rand Corporation back in about 1950, but was actually given its name by a very famous mathematician, Alvin Tucker, in a book by that title. And so in more recent times, this notion of a prisoner's dilemma has actually been used in the context of climate change by economists to talk about how we actually solve this problem in a rational way. So first, the concept of the prisoner's dilemma is if I have a crime that's been committed and I have arrested two different people that I think were responsible. And the district attorney goes to each one of them and says, if you tell me that the other guy was the one who did the crime, you will get off free and he will have to go to jail for 10 years. Okay? So if you confess and tell on your opponent, you don't have to go to jail, your score is 0, your opponent goes to jail for 10 years. But the same is true of him. If he tells on you, he gets off free and you go to jail for 10 years. The problem is if you both try and rat on each other, you both go to jail for 5 years. But if you both stay silent and don't do anything, if you cooperate, you only each go to jail for 1 year. So you can formulate this problem in many different ways with sort of different metrics for the penalties and benefits and play this kind of a game. But clearly the best solution for both parties is to say nothing, cooperate. But self-interest typically drives people to do this. I don't want to go to prison at all, so I'm going to say he did it. And then I get free and he gets the 10 years. But what we see is if both people are motivated in the same way, they'll both wind up with 5 years. So this is the typical prisoner's dilemma. But it can be reformulated in the context of global warming, where instead of going to jail, you lose some % of your gross domestic product per capita as your penalty. And so if you cut emissions and cooperate, you can have benefits and penalties. If you refuse to act and look only after your self-interest, and then the combinations, again, tell you that the best solution for all would be for all parties to cooperate. But self-interest typically will drive you to look after your own self-interest, ignore that, and the consequence is greater penalties for all. The scenario that's been worked out as to how do you solve this problem and essentially make people do the right choices was his recommendation that you start off being nice. You set an example. As I said, the United States must set an example for the world. and lead in this. And if you set up an example, then people will perhaps be willing to follow you. If they don't follow you, and they're still acting in their own self-interest, his recommendation is that your next step, you have to retaliate. Tariffs, embargoes, some penalty measure that will hopefully change their behavior to go back and cooperate. And if indeed the other party cooperates, you should forgive them and also remove the penalties and go back to being collaborative. And finally, you have to sort of announce ahead of time that this is the strategy I will use. If you cooperate, if you share the burden, if you don't simply look after your own self-interests, we'll all get along. But if you choose to ignore the realities and look after only your own self-interests, we will punish you in some way to bring you back to the fold. This is perhaps easier to outline than it is to implement in a global world with the realities we face. But it gives some sense of how we should do that. And so you can find similar publications. This is from the Proceedings of the National Academy of Sciences, fairly recently, which again invokes models of the prisoner's dilemma to try and see, what's the optimum way to solve this problem, and what kinds of problems might we get into. Here you can see where there's this critical threshold of carbon, and it has to do with how we perceive the risks. If we think the risk is severe, and that the risk is immediate, will happen very soon, we are more likely to cooperate than if we're uncertain about the risks, or its timing, or how bad things might be. And the problem with global warming is it's not like an earthquake. It's not like a tsunami, where when it hits, or a volcano exploding. It's not like something that's so instantaneous. It's a very slow and gradual process. And so the general perception is, we have lots of time. We can fix this later. New technologies will come up. The reality is quite different. So this leads to my third topic, which is on civil disobedience, which I say is every scientist now personal dilemma. And it derives from Henry David Thoreau, who was a very interesting person, author, poet, philosopher, etc., who pioneered nature studies in the United States, and for a time lived for 2 years in a little tiny one-room cabin on something called Walden Pond in Concord, Massachusetts, which is only an hour or two drive from where Hunter Sensei and I now live and work. And he recorded, while he was in Walden Pond, the time when different plants would flower, or trees like your cherry blossoms that are just blossoming now. And it's interesting, someone went back and has now used his notebooks to show that the time of blooming has moved up because the climate is warmer. So just a paper, again, from January of this year, using Thoreau's notebook records as one more piece of evidence that the climate is changing and warming. So this is Thoreau in his little one-room cabin on Walden Pond, and he was very concerned about slavery in the United States at the time he wrote this, but it applies universally, and he comments that unjust laws exist as a reality statement. And then he poses the question, are we content to obey them? We know they're unjust, but we just put up with it, we'll tolerate it. Or shall we endeavor to amend them? We know they're wrong, so let's try and change them. But while we try to change them, do we obey them until we have succeeded? So we know they're wrong, but we're going to work hard to change them to correct those laws, and we'll obey the laws while we do that. Or, finally, shall we transgress them all at once? Is it so bad and so unjust that we cannot wait for the process to change them in an orderly and typical fashion, that we simply have to violate the law? And then he says, men recognize the right of revolution, and talks about how when governments are unjust or inefficient in their tyranny, and it's undurable, you have the right to revolt. So he talks about these themes, again, in the context of perhaps other subject matter, but they're, again, food for thought about how one decides to act, and whether or not to be a law-abiding citizen, or whether it's time to revolt. So you read that, and then you come to that same issue of Nature, published in 2012, where this is a sort of address the scientists, be persuasive, be brave, be arrested if necessary, be civil disobedient, violate the laws. And he talks about this in the context here. This is Bill McKibben, the 350.org founder, and Jim Hansen. And he talks about, and they were arrested for protesting that Keystone pipeline I mentioned that's supposed to bring the oil from the Alberta tar sands to the Gulf Coast. So those scientists and activists are actually out getting arrested today, trying to help stop this. And the question now is, how much of the scientific community perhaps needs to follow in their footsteps? One last piece I won't go into, but just to cite more as a references, by a philosopher, Stephen Gardner, at WashU, who has a very interesting survey article on ethics and global climate change, and talks about how at the heart of this problem, it really is an ethical dilemma that we face. Again, excellent source for reading. So one of the solutions that's been proposed to allow us to continue to burn fossil fuels is this idea of carbon sequestration. This is not to be confused with the problem in the government and the budget in the United States, where we are now in a mode where each of the budgets for the different departments in the government are being sequestered or hidden or not allowed to be spent, which is cutting budgets everywhere. So this is a big topic at the moment for budget reasons. But carbon sequestration is the notion that we can do the same thing. We can somehow take the carbon dioxide we create from burning fossil fuels and hide it. Keep it away from the environment where it won't cause global warming. So here's our big mountains of coal. They go into the power plants. And the idea is we now take the CO2 that we can somehow capture at the power plant, perhaps. And they show the various things you could do with it. Like over here, I like this one. Industrial uses and food products. There's our Coca-Cola. So we could probably make a lot of Coca-Cola with all the CO2 that is produced by gigatons of coal burning. This is not real. But the other notion is that we put it back in the ground. It's already being used. We essentially turn it into liquid carbon dioxide, pump it down into old oil wells that aren't producing, and that liquid carbon dioxide helps to extract what oil remains from those deposits. The other is to simply pump this liquid carbon dioxide into various geological formations, into saline formations, so it dissolves in salt water deposits that exist in the ground. Put it into old oil and gas wells that we've taken everything out of, so we now fill them up with CO2. But the other things they show, this word is seal, S-E-A-L. It implies that we have some geologic formations that serve like a cork in the bottle, that are going to keep all that carbon dioxide in the ground for a long, long time and won't ever let it pop out and leak out. So the question is, how realistic and how expensive and efficient might this be, and how risky would it be? It includes ideas for actually storing that carbon dioxide in the deep sea in various ways. So there is scientific studies on that. Another notion for putting the carbon dioxide in the oceans deliberately to try and keep it away. And again, interestingly, people have actually done detailed analysis of sort of the fundamental chemical energetics, the physical chemistry involved here, as to what it costs post-combustion. You've already burned the coal and oil and gas. Now how somehow you have to capture the carbon dioxide before you can even begin to think about sequestering it. And some of those schemes include crazy notions, I would call them, maybe. This is a company called Carbon Engineering in Canada. This is actually a cartoon. This isn't a real device, but for scale, that's a pickup truck and a person. They are proposing to build these giant machines that literally take the carbon dioxide out of the air and liquefy it, and then put it off someplace to hide it. So you can imagine there's huge, huge areas of the world covered by these giant machines, just simply trying to suck CO2 out of the air. This begins to become something called geoengineering, where we deliberately are trying to engineer our climate by directly manipulating it. And there are a variety of schemes and proposals for how one might do this, and it's been studied by the Royal Society, US SOMAR Conference, and others. So there are many, many studies you can go and look at that sort of analyze the pros and cons of these. One of the schemes is simply to put sunglasses on the Earth. Basically go out somewhere between the sun and the Earth and build a giant array of mirrors that will reflect sunlight away from the Earth and reduce the solar energy that comes in that drives the global warming. Can you imagine how expensive and complicated such a scheme will be? Another plan is to try and reproduce what volcanoes do, which would be to fly airplanes way up in the atmosphere and essentially dump sulfuric acid as an aerosol high up in the air. because the sulfuric acid then serves to, again, reflect sunlight. But can you imagine fleets of airplanes? Or maybe every time you go on an airplane, part of the plane is spitting sulfuric acid out to try and do this. And again, it's to mimic what we see naturally. So this was from Pinatubo's eruption in 1991. It threw up, enormous clouds of dust and enormous amounts of these sulfur compounds into the atmosphere, and actually cooled the planet for about 3 years. The temperature, global temperature, went down following this one eruption. So this is the model. They say, okay, well, this occurs naturally. Maybe mankind could adopt the same thing. These schemes I don't find terribly comforting. And the other problem is, in particular, the ones I've listed don't address this problem of the increase in carbon dioxide. They decrease the incoming energy, but the carbon dioxide would continue to increase in the atmosphere, which also means it will continue to dissolve in the oceans, which means it will continue to affect marine life, which again you'll hear from later this afternoon. So I would propose an alternative that I call carbon sequestration, with the idea we're going to put this all in the sea, to buy time until the world can solve the problem in a real way. This is not meant to be a long-term solution. And it comes from an interesting notion proposed by an oceanographer named John Martin in essentially a bag lunch talk he gave. They have this thing in Woods Hole where people come and give informal seminars at lunchtime while people eat their lunch. And he made this statement during that little talk about, give me half a tanker of iron and I'll give you an ice age. He was basically proposing that he could artificially induce global cooling to create an ice age. And what he was proposing was to add iron to the ocean. And this little cartoon in the article that describes this talk he gave shows him dumping bottles of this stuff called geritol. It's an iron supplement that people take to increase the iron in their diet. So here he's dumping bottles of this in the ocean to do this. And he actually was the first to go off and test this. He's first author on this paper, testing the iron hypothesis by inducing phytoplankton growth, causing a giant bloom. But what he's talking about, you fill up one of these things with some iron solution and go dump it in the ocean, and you can create one of these. So from outer space, from a satellite, you can detect this beautiful blue-green color of a plankton bloom off the coast of Argentina, which occurs naturally. He simply wanted to go and do these artificially on a large scale, and then drive the biological pump that Hunter Sensei described, which takes atmospheric carbon and through a very complex process winds up eventually sequestering it in the deep waters of the ocean, where it would remain isolated from the atmosphere for hundreds, if not thousands of years. And so the idea is of something called the iron hypothesis, that minerals and dust, like the yellow dust from China that's now blowing into Japan, flows out over the oceans and settles into the water, where iron dust turns into dissolved iron and becomes a nutrient to allow the growth of phytoplankton, which when they die sink through the biological pump mechanism to put the carbon that was in the atmosphere at the bottom of the sea. So the reason that this is the case is I have to go back and look at the elemental composition of marine phytoplankton. This is a 2003 paper. There's a complex formula down here that I've blown up on this page. So if you count up how many atoms of each type does it take to make a phytoplankton, you find that carbon is number one. So in this ratio, there's 124 atoms of carbon. Next is nitrogen, phosphorus, sulfur, potassium, magnesium, calcium. But these are in parentheses, you multiply them by 1,000. And then at a lower scale, you have strontium, iron at 7.5, zinc, copper, etc. So if you actually take the ratio of these two with this involved, you essentially have 16,500 carbon atoms in a cell of a phytoplankton for every 1 atom of iron. So they need very, very trace amounts of iron, and they can put a lot of carbon that they fix from the atmosphere from CO2 into that cell. This was originally described as something called the Redfield ratio, named after oceanographer Alfred Redfield. In 1934, he looked at the primary elements and their ratios, which were about 106 carbon to 16 nitrogen to 1 phosphorus. And it's his name that's on the front of the laboratory where you saw this picture taken earlier, where we held our first kickoff meeting for this symposium with the steering committee. So we see evidence of this all the time. So these are satellite images of dust plumes coming off the coast of Oman or off the oceans in Alaska, Pakistan, West Africa. The problem is most of that dust settles fairly near to shore. It doesn't reach the deep oceans or the outer oceans. And so oftentimes, those parts of the ocean are iron limited. They have all the other nutrients needed to make algae, but they just lack iron. And interestingly, this is a paper just published this month in March. As the glaciers in Greenland and elsewhere begin to melt, they're also introducing enormous amounts of iron into the sea. So it'll be interesting to see what happens to phytoplankton growth in those areas as well. Yet another example from one of the early experiments of inducing a massive phytoplankton bloom by such a method. But a number of people, again, sort of were skeptic about this. Kevin Ulmer is a colleague at Woods Hole who published Will Iron Fertilization Work? Is it going to work on a large enough scale? Does it really address the problem? So again, there have been studies by a number of different organizations and bodies trying to look at this as whether it's a realistic alternative. This one by Sally Chisholm from MIT and others, that again explores the biological pump for sequestering CO2 in the deep sea. The problem is there have been very few experiments. This is a global map that lists most of them. You'll see that many are clustered in the Southern Ocean off of Antarctica, where there's very nutrient-rich waters but no iron. There are others in northern latitudes up here and a few in sort of equatorial regions. But there's only been perhaps 13 such experiments. They're listed here, not for you to read. They give sort of the details of the scale and sort of a timeline here of sort of the evolution of this whole field. The general consensus of that one report was that they decided this really wasn't a realistic solution and that we should really not worry about it so much, which I sort of disagree with. But they also said at least that ocean fertilization research should not be halted and should be continued. And again, my colleague Kevin Ulmer called into question moving forward. A lot of this was due to the fact that this idea of carbon credits. So if I can start a company that somehow can sequester CO2 by planting trees in forests or some mechanism like fertilizing the ocean, I can sell those credits to the companies that are creating carbon dioxide by burning fossil fuels and make money. So a number of companies were created a decade or so ago to try and exploit this. And so I think a lot of the criticism by Ken and others was trying to limit those and only allow really scientific experiments that were well-founded and would result in scientific data, and they provide a list of criteria that they felt should be met to allow these to occur. Other papers that continue to stress why we need to do more research, we just don't understand this process well enough to really utilize it. But then this past summer, this was published I think in August, there were the results of one of the more recent experiments, one called IFIX. It was the European Iron Fertilization Experiment. Published some very encouraging results. In their data from this one attempt, they conservatively measured a ratio of carbon to iron of roughly 13,000, with an error of about 1,000. But in their supplementary material, they say, for a variety of reasons, this is highly conservative. That number is probably closer to 30,000, which means there's an enormous amplification. For a tiny amount of iron introduced, you can generate 30,000-fold more carbon, potentially, that would be sequestered. So this was a real glimmer of hope that this might indeed work. The problem was, last summer, this happened. So here's an individual named Russ George. He was the founder of one of these companies called Planktos that was going to try to make money by doing this. In 2008, when the global stock markets crashed, Planktos went out of business. Russ George is still around. And he actually did an experiment last summer off the coast of British Columbia where he dumped iron in the ocean and created this bloom, with a question mark after it, iron fertilization bloom. Oops. This is August 29th, 2012. So there were enormous headlines saying, because this was not a scientific experiment, he just went off and did this. called civil disobedience on one hand. You know, no permits, no approvals, no ask permission, just go dump iron in the ocean. See if you can make a balloon. And he did, and I'll get back to that a little bit more. So my sense is the problem that we have with the prior experiments here, first of all, there were too few of them. We need many, many, many more experiments to replicate this if we're going to make advances. So only about a dozen experiments in 20 years. The other problem is it was difficult to follow the full cycle of the balloon, from the time you introduce the iron until all of that carbon supposedly has reached the deep sea, is more than a typical time you can spend on a ship to watch it happen. So it's a limitation of human shipboard tracking and station keeping. You know, after 45 days, the crew mutinies. They don't want to stay around anymore. The other problem is that the measurements they made weren't comprehensive enough. They try and fertilize large areas of the ocean, and it's really the full depth of the water column, from the surface all the way to the bottom, that then has to be monitored across this very large area. So it's a huge volume of seawater that you need to monitor. And if you just have one ship, it's very hard to run around and make all those measurements. And the sensors and measurements they made weren't really comprehensive enough. So there's a limitation there. And again, this ability to just simply run around chasing a balloon. They also didn't fully exploit satellite capability and remote sensing to track and monitor these, make measurements. And the other thing that was very frustrating is they didn't really report the results very quickly at all. For example, that IFIX experiment was actually conducted in 2004. The paper I just showed you was published in August of 2012. We can't wait that long to get data. So this is just a schematic where the size of these little squares roughly gives you an indication of the surface area. So this is 72 kilometers square for this first iron experiment that was done in '93. So they've all been fairly small. These big blue ones were proposed experiments by some of these companies, but were never actually conducted because the companies effectively have gone out of business. But we indeed need to move from very small scale to larger scale experiments to see whether this phenomenon can be scaled effectively. So in the future, we also need to do very efficient baseline monitoring. Before you dump the iron in, who is living there? What are the organisms in the entire water column from the surface to the bottom? What fish are there? What zooplankton? What phytoplankton are there? What's the chemistry of the water? So this is our starting baseline condition. Then we introduce our iron, and then follow the history for the entire cycle of the balloon, from the beginning until the very end. Integrated tightly with remote sensing. So we're also tracking this from satellites in space at the same time to be able to cover large areas very efficiently. And to do this, we can't use conventional oceanography with scientists on ships running around chasing things. It really has to go to a new world of robotic, autonomous samplers and motherships that essentially will be the fleet that will do this. And the other key ingredient is that we have to release the data immediately. So I was, part of that book called the Human Genome Project to sequence the human genome. And very early in the history of that, there was something called the Bermuda Agreement, where all the scientists involved in generating the sequence data for the human genome agreed to release their data 24 hours after it came off the DNA sequencing machines. So unlike sort of conventional history where scientists generate their data and then they're allowed to sort of sit on it until they reduce it and analyze it and eventually publish it before they release the full data, here everyone recognized that it was critically important to have immediate data release on the internet globally to anybody who wanted to access and use that data to help analyze and interpret and use it. And I think we have to apply the same thing here if we want to make real progress. And then we have to repeat this over and over again, refine and repeat, improve our models and our ability to do this. So one way to do this, and it was used in IFIX, sort of can be modeled on a river. So this is a river flowing through a national park near Boulder, Colorado, where I'm currently consulting. And you can see how rivers meander back and forth through the landscape. Oops, sorry. Hit the wrong button. Well, the oceans do the same thing. So here's Japan, the Kuroshio Current that flows up along your east coast. And sometimes these meanders get so big that it spins off little gyres, little bodies of water that are spinning around in the ocean, here, here, and everywhere else. And they serve as nice sort of giant test tubes for doing experiments, that you can go do your iron fertilization in this little gyre, and it basically limits where that experiment is. It's not going to just wander all away. And And so we can exploit the fact that these gyres are constantly being generated and spun off of currents like the Croatia or the Gulf Stream, North Atlantic, and use those as an interesting test bed for this method. And the technology we need is similar to what Hunter Sensei showed you. This is one of the graphs from a proposal for a global biogeochemical flux program that would monitor the carbon flow. But a lot of it is based on fixed arrays. So these are moorings that are anchored to the bottom of the sea. So if you have a plume that's drifting with currents and moving, this is not a good way to follow them. But one component of this is these things that sort of look like torpedoes that are zooming around underneath. These are autonomous underwater vehicles. You can program them to go to a certain place or depth, make measurements, take data, follow some particular signature, and then come back and report the data. And it's similar to these that are not active floats. These are called the Argo system. So there are now over 3,600 of these little floats. All these little dots are where one of these Argo floats are. They're floating around in the ocean. They're programmed to sink to a certain depth, turn around, come back to the surface, and then transmit their data back to a global network. So we were able to collect global information on the oceans by this system. The problem is each of these little floats costs $30,000 a piece, and right now they don't measure anything interesting from a biological or biogeochemical perspective. They measure salinity, temperature, and depth. So they can help us monitor what the currents are, and changes in ocean temperature, and things of that sort. But they won't help us with tracking the carbon. So we need a new generation of things sort of like this, but that are also autonomous. And one of the things, as I say, we need really a mothership that it replaces the conventional oceanographic research ship with no people. It's a big mothership, and it sends out a fleet of these little torpedoes. And interestingly, the technology now exists where they can come back home by themselves and dock, as you'll see in this little video clip, recharge their batteries, offload data, and potentially offload samples they've collected. So here you can see one of these AUVs, autonomous underwater vehicles. And it's going back to the mothership, plugging in, and it will download its data, recharge its batteries, upload a new program of what to go next or what sampling to do the next day. And so I think this is where the future lies, not just for this program, but many other aspects of oceanography, is fully capable robotic systems that can explore the oceans in a way that humans have a very difficult time with. The problem, though, is that we do face a bunch of international regulations that attempt to regulate the commons. So there are the United Nations conventions on biological diversity, which basically says you're not allowed to go around and mess with ecosystems and change them deliberately, trying to protect ecosystems from pollution. Is this kind of experiment with iron fertilization, pollution or not? There's also things that try and prevent people from using the ocean as a dumping ground for waste. Is that what this is if we do these experiments? And then there are other law of the sea conventions that try again to put laws in effect that govern our global warming situation. But who enforces them? Who decides? And if these reviews and permits become too burdensome to conduct the experiments, do we follow them, or again, do we become civil disobedient? So again, other papers in energy policy on how to operate in evaluating iron fertilization in the face of conventions and treaties of this sort. And so finally I say, this is really a band-aid for the planet. I don't propose this as a long-term solution at all, but it might buy us some time until the world stops burning fossil fuels. It might also have a few other benefits. This is this year's record tuna sold at auction, 222 kilograms for $1.76 million. I hope all tuna don't become this expensive or I will never eat sushi again. So what we really need to learn is the thing we learned on land, 20,000 years ago or whatever it was, learn to farm the sea. So in the deep ocean, we're still only hunter-gatherers. We go out and catch things in nets and harpoon them and things of that sort. We don't cultivate the ocean. We do aquaculture near shore and other similar things, but in the deep sea, we do none of that. And so despite the lack of fences, which were sort of a necessary feature, we need to learn how to replenish our rapidly decreasing seafood stocks if we want to keep eating food from the sea. And it all begins with the bottom of the food chain. We first have to make the plankton that are eaten by everything else all the way up to the big fish like the tuna that we all love. And the question is sort of what's the right fertilizer and how do we apply it? So we have a lot of catching up to do to learn how to be farmers. The experiment that was done off British Columbia was actually done by a native tribe in British Columbia that was trying to restore their salmon stocks. And they were the ones that, as a village of only 1,000 people, got a bank loan for $1 million to pay Russ George to do that experiment in hopes they could bring back salmon. And the reason for believing it was possible was that whenever there were volcanic eruptions in the Aleutian Island chains in Alaska, they would release enormous clouds of dust. And every 3 years after this kind of event, the salmon would be back in abundance. So the native tribes had witnessed this over and over through their history and believed that if artificially we could do the same, perhaps we could induce fish to grow. So I fly over the central United States between Boston and Colorado on a regular basis, and when you look down, you see this enormous agriculture system we've built up. These are these irrigation circles. They're huge things. You know, our sophistication in land-based agriculture is enormous, and we need to apply the same in the oceans. So, in summary, we face an inconvenient truth that arises from this tragedy of the commons, leaving us with a prisoner's dilemma that may eventually require civil disobedience if we're to save planet Earth. And the question remains then, will the world's oceans become another victim and acidify and change, or might we be able to use them to help us, at least in the short term, to buy some time? So, I would urge you all to get involved, to think about this on a daily basis, engage in discussion with your friends, your colleagues, your family, anyone who will talk about it. Don't let a day go by where you don't think about it. Even though it's not a critical crisis like an earthquake or like a tsunami, it is one that needs to be thought about on a regular basis. This URL for sequester.org is a new nonprofit company that I have just formed. If you go to this website today, there's nothing there yet, but it will become a resource for further information and a point of contact if you're interested further. And I believe that the presentation will be available in formats where, again, you can go through this and pull out those various references if you want to pursue them further, put together a study group or a course or a class. And so finally, just as Jim Hansen was inspired by his granddaughters, these are my two. And I won't go with that one. And so I will simply stop there and say thank you very much. What, you see this? You can see. Okay. All right. So turn the lights down again, please. So I mentioned that if there was time, I have to start this. This is a short minute, about 4-minute trailer from a movie called Chasing Ice that, as I say, has now appeared in some theaters in the United States. I've already seen it. It was produced by someone who actually lives in Boulder, Colorado, where I'm currently working, so maybe that was why I was in the theater. But the organization behind this is called the Extreme Ice Survey. And what they have done is placed remote cameras in, I think, 26 locations of glaciers from Alaska to Greenland to Iceland that are simply bolted into the sides of the mountain and do time-lapse imaging of the glaciers to watch them and see how they are disappearing. Because it's a process, again, it's slow on a human time scale. And so it's necessary to follow them over many years. This particular clip from the movie is of the world's largest glacier, and it witnesses what's called calving, essentially the breaking off of the front end of the glacier to create icebergs on a scale that has never been observed by humans before. And in the beginning of the film, you'll see it's rather awesome, but there's hardly any way to get scale. But you'll get an appreciation for that later in the film when they superimpose the lower half of Manhattan Island in New York is the size of a piece of ice, or even larger, this piece of ice is breaking off. And the height is equal to the height of the skyscrapers. It's just staggering. So I would just leave you with this as just one more reminder that climate change and global warming is very real. It's very scary, and that we need to do something about it. So let me see if this will work. just the volume.
I'm on the phone with Jim on one of our regular check-ins. Jim, just nothing's happening.
It's going well. We had some serious bouts of wind, but other than that, things are fairly well set up.
It's starting, Adam. I think. Adam, it's starting.
Let me call you back.
All back.
Okay, bye.
Yeah. And that V section right there. Holy shit, look at that big bird rolling. All four right? Look at that. You see how, look at the whole thing.
Faces 300, sometimes 400 feet tall. Pieces of ice were shooting up out of the ocean at 600 feet and then falling. The only way that you can really try to put it into scale with human reference is if you imagine Manhattan. And all of a sudden, all of those buildings just start to rumble and quake and peel off and just fall over and roll around. This whole massive city just breaking apart in front of your eyes. We're just observers, these two little dots on the side of the mountain. And we watched and recorded the largest witness calving event ever caught on tape.
So how big was this calving event that we just looked at? We'll resort to some illustrations again to give you a sense of scale. It's as if the entire lower tip of Manhattan broke off, except that the thickness, the height of it, is equivalent to buildings that are 2.5 or 3 times higher than they are. Miraculous, horrible, scary thing. I don't know that anybody's really seen the miracle and horror of that. It took 100 years for it to retreat 8 miles from 1900 to 2000. From 2000 to 2010, it retreated 9 miles. So in 10 years, it retreated more than it had in the previous 100.
Thank you, Gabe.
Thank you very much. It was a great talk regarding carbon dioxide, and in the end, it's a horrible, real things happening with this Earth. So, of course, in the end, so Mr. Toyo came Then he's gonna pass our sincere thank you break to him.
To express our sincere appreciation as a plenary speaker of the Toyo University 125th Anniversary International Symposium. Thank you very much, Dr. Ulmer. Okay.
Thank you very much. So we are going to take coffee break maybe by 4:20. So 4시 20분 만에